Thank you very much and welcome also from my side to this labcast on iprm-PASEF. This labcast is for current timsTOF fleX users who want to learn more about and implement the newly launched iprm-PASEF workflow. If you are interested in other introductory labcasts for multi imaging, including the timsTOF fleX or other platforms, please check out our webinars page. In collaborative studies using mass spectrometry imaging, the typical question is to identify the molecules that discriminate between different tissue states. CCS-enabled multi-imaging allows to extract those features from complex datasets. However, an accurate annotation of those molecular identities requires in-depth mass spectrometric fragmentation analysis. To provide an answer to these questions, I will introduce now iprm-PASEF and show you the workflow in action. iprm-PASEF is our new workflow for targeted multiplexed multi-MS/MS imaging. We offer a full software-supported workflow that allows you to acquire, analyze, and annotate MS/MS imaging data for up to 25 precursors in a single acquisition. iprm-PASEF is based on the PRM-PASEF acquisition mode of the timsTOF fleX system. In PRM, a targeted ion population is isolated using a quadrupole, fragmented in the collision cell, and the resulting fragments are analyzed using high mass resolution. We combine this with PASEF, in which we use ion mobility to separate ions in space and time before entering them into the quadrupole, so that from a single MOIDI acquisition, which in an imaging experiment would be a pixel, multiple precursors can be fragmented. The workflow that we offer starts off with a regular CCS-enabled multi-imaging acquisition that we analyze in SkillsLab. Here, we use the direct feature finding to find and select molecules of interest which we want to use as fragmentation precursors. Subsequently, those precursors are transferred to the TIMS control acquisition software for the MS2 measurement. The precursors are then annotated in SkillsLab on MS2 level, based on the rule-based lipid annotation or targeted annotation with spectral library and powered by Metaboscape. Today, we want to demonstrate this workflow for red brain cerebellum, where we started with the CCS-enabled MOIDI2 run in negative ion mode at 20 micrometer spatial resolution to identify our feature of interest in mass and CCS dimension, as shown here in the heat map plot. Enabled by the SmartBeam 3D laser, the pixel was divided into 4 subpixels, where the first quadrant was used for MS1 acquisition, and the remaining 3 quadrants are available for following iprm-PASEF runs using a laser pitch offset. We will start with the analysis and precursor definition in SkillsLab, set up the iprm-PASEF run for region of interest subset in TIMS control, and finally analyze the data on MS2 level in SkillsLab. And with this, we jump over to the software part. To set up the iprm-PASEF experiment, we first need to define our precursors of interest. Therefore, we start with the analysis of the TIMS MS1 run in SkillsLab. In the first step, we run the direct feature finding algorithm, which can be found under Tools. Here, we select the GX-Cube feature finding, which also includes the CCS information. Define your spatial smoothing and coverage according to your needs, as well as the intensity threshold, and start the feature finding. After the feature finding, we additionally started a PCA analysis. The PCA analysis hereby provides us with one component which is specific for the white matter of the cerebellum. In the score plots, we can now use this information to define pixels that should be used to define the region of the white matter. We now switch to the loading plot. We can extract information about the features that are highly abundant in the white matter. We create a feature list from those features and use this for further analysis. In the feature table, we can now explore those features. We can filter them according to our intensity distribution and also to the PCA loadings results. In order to get a first idea of the identity of those features, we can run a molecular annotation. If you want to learn how you can set up the Metalscape annotation pipeline in Skills Lab, please follow the QR code on the right. It will guide you to a training video with detailed instructions. In this case, we want to run the lipid species annotation, which is hereby exclusively based on MS and CCS information. As in this case, the dataset does not contain any MS information. We get exclusively an annotation on the lipid species as well as the total combination of the fatty acid chains. In order to further reduce the number of features for the iprm-PASEF experiments, we now select the annotated features and filter them by their overall intensity as well as their PCA loading scores. By doing so, we now have a reduced set of features that we want to use for our iprm-PASEF experiment. For this export, you find the option to export iprm-PASEF parameters in the top left corner of the feature table. In this window, you will find now the features listed according to their mobility values. Features that are overlaying in the mobility dimension or with windows that are too close together to guarantee a proper mass isolation are displayed here in red. Those conflicts can be reduced by either deselect the features that are delimiting the isolation or by using the auto-resolve functionality. The auto-resolve functionality shrinks down the mobility windows while ensuring that the center of the mobility feature is still within the isolation window. In the end, you can export those parameters either as in CSV or an SPP file. For the SPP file, you can link the region information. In this case, we only want to select the white matter to conduct the iprm-PASEF experiment. In the next step, I will show you how you can now load this information into timsControl. After we have now defined our analytes of interest for the iprm-PASEF experiment, we now want to have a look on what changes in timsControl in terms of the iprm-PASEF scan mode. After you have updated your software to timsControl 6.0, you can find a new scan mode which is called PM-PASEF in the MS settings dialog. For this experiment, we started with the multi-TIMS MS1 acquisition method, which we now additionally need to tune for our MS fragmentation experiment. Here, the first thing that we need to do is to reduce the scan begin in order to also see our fragment masses. Additionally to adapting the M over the scan range, we now want to ensure proper ion transmission of both our precursors and our fragment masses through our timsTOF instrument. For this, we have a closer look at the tune page to adapt the collision cell and the focus pre-TOF settings according to the needs of our analytes. In this case, we want to reduce the collision RF value as well as the transfer time in the focus pre-TOF settings. Those adaptations ensure now for us a proper ion transmission. The main difference for the iprm-PASEF scan mode can be found in the MS tab of the instrument software. In this tab, we can define the iprm-PASEF precursors as well as the isolation and fragmentation settings. By opening the iprm-PASEF window editor, we can import the SPP file which we have previously exported from Skills Lab. timsControl now extracts the precursor information, including the centered masses as well as the mobility begin and end values. In case of too narrow or too close mobility windows, timsControl provides you with a yellow warning about potential risk of compromised data quality. In order to reduce the risk of compromised data quality, you can still delete single features from your list or manually define the mobility window. If all precursor windows are valid for acquisition, timsControl provides you with a green indication. On the left side of the iprm-PASEF window editor, you can open a previously recorded TIMS MS1 analysis in order to review the overlay of your mobility features with your previously recorded analysis. If you're happy with the selection of your mobility precursor windows, you can apply the precursor table and follow with the definition of the isolation and fragmentation settings. Here you have the option to select between the M/Z based isolation and fragmentation settings, which allow a maximum of 15 precursors per acquisition, and the mobility-based isolation and fragmentation settings, which allows to use up to 25 precursors for your analysis. For today's experiment, we select the M/Z based isolation and fragmentation. Here we can define the profile that is used for the definition of the isolation width and the fragmentation energy settings. By defining a profile for in this case 3 different base parameters for both values, we've now an interpolation for precursors in between of those base parameters. After the definition of your iprm-PASEF method, ensure a proper calibration of your instrument. To calibrate the M/Z dimension, accumulate a number of spectra to the sum buffer and use this to calibrate your M/Z dimension over the whole mass range of your analytes and fragments. After you have ensured proper calibration of the M/Z dimension, switch for the mobility calibration toward the electrospray mode. Ensure a steady flow of the Q-mix and calibrate the mobility dimension based on the calibrant signals. Precise calibration of the mobility dimension is mandatory in order to also ensure a precise isolation of the precursor windows. After calibrating the instrument, we can switch towards the fleX imaging software, where we have still open the TIMS MS1 imaging run. In the first step, we create a copy of the imaging sequence and then change the acquisition method for the new defined iprm-PASEF method. In this case, we do not want to run the full region for the iprm-PASEF imaging run. Therefore, we first delete the previous region. And import the region from the SPP file, which we have exported from Skills Lab. As you can see, this region now exclusively describes the white matter of the brain. Finally, we want to start our iprm-PASEF imaging run. In this case, we define an offset of 10 micrometer in the x dimension to measure the second quadrant of our pixel. During the acquisition and TIMS control, we see now the distribution of the signals for the precursors and their fragments, but all on the line of the mobility of the precursor. The colored mass spectrum at the bottom now sums up all 11 fragmentation experiments. After the iprm-PASEF acquisition finished, we started a new import into Skills Lab. Already during the import, Skills Lab now recognizes that the selected dataset is an iprm-PASEF file and will create an iprm-PASEF project. As you can see, in this case the imported region is solely based on the white matter of the cerebellum. The feature finding can be triggered hereby now directly during the import. And again, we select the T-Rex Cube feature finding algorithm, which includes also the CCS information. Also, we start directly the extraction of the CCS images. After the import finished, we can display the heat map of the iprm-PASEF experiment in the feature navigator. Here we see towards the right the intensities for all precursor ions, and on the same mobility axis we also see the intensities of the respective fragment ions. To focus for the explanation, we now zoom in on one specific feature. We can now display the results of the feature finding, and we can see that we have now two different types of features. Features that lay within the isolation window of the mass and mobility dimension are defined as a precursor feature. On the other side, all features towards lower masses are described as fragment features. In the next step, we now want to run again the molecular annotation. Also in this case, we want to run a rule-based lipid species annotation. For the annotation of iprm-PASEF data, we ensure in MetaboScape that we only allow annotations that are validated by MS-MS spectra, and also ensure that we have a proper MS-MS score defined next over M/Z, millisigma, and CCS score. After the task finished, we can see that we have now an annotation for our feature as PA18018.1. If you now want to review the details of the annotation, we can activate the Show Detailed Feature Information option. In this tab, we can now see that we have actually two different annotations, one as PA361 and one as PA18018.1 on the molecular species level. We now activate this annotation and can explore in the fragment tabs which fragments were actually used to identify the compound. For the species level, we can see that the head group fragment was found at the mass of 152.99. Additionally, the fatty acid chain composition was confirmed by the detection of the 18-0 and 18-1 fatty acid change at the masses of 281 and 283. If we now minimize the feature table, we can confirm the annotation additionally by the spatial information provided by the precursor as well as for its fragments. In the last step, we want to run the annotation on all detected features. Therefore, we select the complete feature table and restart the annotation. As you can see, for this analysis, 7 of the precursors were successfully annotated. For the lipid PS42-1, we get actually 2 suggestions for respective fatty acid combinations. In this case, for both annotations, the respective fragments were detected. Hence, we can assume that both lipids were present in the precursor window. Altogether, I hope that I demonstrated that iprm-PASEF enables you to obtain accurate molecular identifications by multiplexed MS-MS imaging within an integrated software workflow. If you want to start with iprm-PASEF for your own research, check out the latest updates for TIMS Control 6.0, Metaboscape 2025, and Skills Lab 2025A using the QR code provided. I thank you for your attention, and I'm happy to answer all your questions in the following Q&A.